All right, so number 4. Which point or points on the graph of y equals 4 minus x squared is or are closest to the point 0, comma 2? Huh? Okay. I need a point here, or multiple points, that's closest to 0, comma 2. So I could have a point here with some distance of that, some point here with a distance of that. I am trying to find what, first of all? A maximum or a minimum? Closest, I think I want to find a minimum. And I want to find a minimum, well, distance. Here's what we're going to do. I'm going to take a point on that parabola. I'm going to call it x comma y. I want to minimize the distance. The distance between x comma y and 0 comma 2. Hopefully you remember the distance formula that says d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. I want to find the distance between x comma y and 0 comma 2. So that's going to look like d equals the square root of, x minus 0 squared plus y minus 2 squared. And that's my primary equation. Here's our secondary equation. Take a moment, plug that in for y, and then do some foiling and clean up the stuff inside your root. You're going to end with d equals the square root of what? And send that into Edpuzzle. Hello. I'm going to plug that in for y. I'm going to get d equals the square root of x squared plus 4 minus x squared minus 2 squared. Oh, running out of space. D equals square root of x squared plus 2 minus x squared squared. Write it out twice in FOIL. D equals x squared plus 2 minus x squared times 2 minus x squared. Oh, I'm coming up here now, I guess. D equals square root of x squared plus 4 minus 2x squared minus 2x squared plus x to the 4th. D equals the square root of, let's see here. This looks like x to the 4th minus 3x squared plus 4. And this is my primary equation. This is now what I want to minimize. And that looks unpleasant because I don't want to deal with the square root. Ugh, that's a pain. We're going to cheat a little bit. Instead of minimizing the distance, I can minimize the distance squared. Let me show you what's going on. Let's say I have x values and I can find a distance. Let's say when x equals 1, my distance is 3. When x equals 2, I'm just making up random numbers here. X equals 2, the distance is 6. X equals 3, the distance is 5. X equals 4, the distance is 2. Just random numbers. At what x value does my minimum distance occur? At x equals 4. If instead I look at the distance squared, I would get values of 9, 36, 25, 4. At what x value is my distance squared, the smallest? It's still at x equals 4. What I can do is I can minimize the distance squared instead, because that's just going to be a nicer formula to work with, and I'm not going to have to worry about dealing with that ugly square root and stuff like that. So, our trick is going to be minimize the distance squared. By the way, as for our domain, x should probably be, let's just focus on this half of the parabola, x should probably be greater than or equal to 0. But I don't really think there's a maximum y value. I mean, I could certainly go below the x-axis. Probably it's not going to give me the closest, distance over there. But there's nothing that says my y has to be bound by something. So my domain is just going to be x is greater than or equal to 0, which means I can't use Canada's test. I'm going to have to go use that global justification here. Okay, distance squared. Let's look at the function f of x equals, square this thing, and we get x to the fourth minus 3x squared plus 4. Find the derivative, and then just stop. Okay, I've got to set this equal to 0. I'm going to do a little bit of factoring because I can. I'm going to say 2x times 2x squared minus 3 equals 0. I'm going to get critical values at x equals 0. And then x equals plus or minus square root of 3 halves. Maybe I'll just leave it like that. And again, if I'm just focusing on the forward half of my parabola, because actually, if I can find a place over here where my distance is minimum, it also has to happen at kind of the reflection over there. Just change the sign of the x-coordinate. Don't worry too much about this. So I'm just going to focus on the positive square root. I'm going to do my number line with a bound there at 0 and a critical value at square root of 3 halves. If you plug in something like 1 to f prime, is f prime positive or negative? Sorry about that. If you plug in 1, you're going to get 4 minus 6, you're going to get something negative. Plug in something bigger than square root of 3 halves, 2 would work, square root of 4, which is 2. You're going to get positive, positive, that region's positive. And we're going to go through our global justification here, because f is decreasing everywhere before square root of 3 halves and increasing everywhere after square root of 3 halves, and tell me how you know you're decreasing and increasing. F will have to have an absolute minimum at x equals square root of 3 halves. Because f is decreasing everywhere before x equals square root of 3 halves. Why? Because f prime is negative there. And increasing everywhere after x equals square root of 3 halves. Since f prime is positive there, f has an absolute minimum at x equals root 3 halves. Take a moment, copy that down. Again, this is our global justification. I know x equals root 3 halves. Y equals 4 minus root 3 halves squared. 4 minus 3 halves, 8 halves minus 3 halves, that's 5 halves. So I think the point is root 3 halves, comma 5 halves. Although, if I have a point at root 3 halves, comma 5 halves, I also have to have a point over here at negative root 3 halves, comma 5 halves, just because of the symmetry of the parabola. And there we go. Anytime we want to minimize distance, that's going to be a pain because of the square root. Let's not do that. Instead, let's minimize the distance squared, and then we don't have to deal with the square root and all the chain rule stuff and that ugliness.